Well, I'm still here. Still here in part one of day 16. And I feel like I'm closer, but still not there. Still don't have a solution. So I think I was thinking about some stuff right near the end of the last stream, and it's something that I can do, which is I think we have to prune paths, because as we see when I do this, did I remove all the breakpoints? I think I did. But if we look at the paths to evaluate as we go through this, even with a simple test, we're causing not to spin, I don't think, but we are causing a lot more paths to be made. Although I don't think we should be spinning. Let me just check that. So we have 2, whoops, and 4, and then 7. And okay, we are starting to get some that are a little bit higher up. Yeah, but the problem is that we just, these are now going over there and down. So it does make progress. But like even here you can see like this one, and that's something that, yeah, we have to think about, because as you're going through the maze and you create new paths, when you make a junction, one that turns is automatically going to cost a lot more than one that stays the same direction. But that doesn't mean as they evolve and you find where they're going to go, that the one that turned actually ends up being less costly. So you can't look at itself and say, well, we got to eliminate those as you're making new paths from a current path. But what you need to do is look at paths that have traversed the way you've gone before. So it does matter to say, if I hit a junction that's already been traversed in the in the direction I am going, and it has how did I say this? If the one that has visited it before has an equal or less cost than what I have, then I should be eliminated. Otherwise, that one should be eliminated. So we do need to keep track of a junction. And this is going to be a little, this is, why can't I type? Sealed record junction. It has a position. It has a direction. And it has a cost. Now the cost is because of the junction, you know, the cost on that path of what it did. Somebody else could hit that junction and have a smaller cost or a greater cost. Okay, this is relative to the, I don't even use reindeer, do I? Yeah, I totally gave up on that idea. but we have a path. Where's the path? Oh, that's this whole big thing that I defined. Never mind. Jeez. Whew. I'm getting loopy on this problem. So what we want to do is we don't want to just store where are we storing this in the the visited junctions. Okay. So that's going to have to change. And of course that breaks the whole world because now here's the fun part. We want to add a junction to the ones that we visited, but we need to know what our cost was when we make this extra thing. And I guess arguably you could say let's think about this a second. It's the path. We're keeping track of the position counts and the number of turns and what our current position is. The visited junction I'm just trying to figure, I mean, I could do it in a messy sort of way. Because the current cost is currently part of a path. And it looks at the traverse positions and the number of turns, which makes sense. But when I'm trying to do it up here, if I say new junction, I put in next position. The direction is going to be fine because I'm going to say it's direction east. But now the cost is going to be a little bit squirrely because it's going to be what the path is going to be once I actually make a new path with the wither. So I have to, I could make junction have a writable cost. But that feels a little janky. It would work. But you notice a visited junction is a hash map, a hash set. And so if the cost would be part of that figuring out of its uniqueness, you know, that would suck. We could do this. That has a current cost. A junction also has a cost. And then what we could do, if we come back up here, we could basically keep track of each one. I mean, this is a little meh, but we could again say what we're going to do here. There. And the same thing well, now what we want to do is we want to say Annie. There. That works too. So this would be going north. This would also be yeah, that didn't turn. Number of turns plus 1. This would be south. And the number of turns 1. And again, this check is just to say we don't care that what direction you hit it. You just somehow on your path came back to it at that position. So this would be going east. We didn't turn. Oh, we had that. Okay. And now we got to do the same for the others. Actually, I'm going to change these all. Get these out of the way. What's scaring me with all this is that even if I get the answer, is what is part 2 going to do? Okay. So this was looking east. South, we don't do anything here. Now what we want to do is I'm going to look east. This is west. And this is south with no turns. Okay, now if we go west, we can hit start. This is going north. This is going south. This is going west, but with no turns. And then finally north. we do that? Seems like a holdover for no reason. Going north, so we didn't have to turn. And we're done there. This is east with turns. This is west with turns. And this is north with no turns. There. Okay. Come on, there you go. Now we have to do the pruning. So this is basically now going to look at new paths and say for a path, is its current junction, does it exist in any of the other paths? And if it does, then we have to determine which one stays and which one goes. And that's going to be how to do this. How to do this succinctly. Well, you want to look at the 0th element of the new paths and then compare it to all the others. If you don't have anything, you could just move on to the next one. If you do, then you may be removing it or others, right? If you're not removing the 0th, you would say, okay, even if I remove others, now we're going to, next time we come through, we look at the first. So I could say for var I is equal to 0, I is less than pass to evaluate count, I plus plus. And we say var first path is equal to pass to evaluated I. Is that correct? And now we want to say var existing paths. These are the ones that already have things. Are the paths to evaluate where that path does not equal the first path, because we don't want to include ourselves, and that path's junctions contains the first paths visiting junctions Ah, crap. Well, yeah, you can't make that a hash set because which I guess is fine. You could just make it an immutable array. And it doesn't change a damn thing down here. Because we never look to say, does it contain it? Well, we do here. And that's just by position. So, okay, that's fine. Okay, fine. Let it tell me what the right syntax is. Length minus 1. Yeah, it's not the range, it's the index. I did it. See? And so we want all the paths that basically contain the last junction that this path has just hit. Okay. And now we have to say if existing paths count is greater than 0. Now we have to do some evaluation. Otherwise, we can just drop out. That's basically saying the path that we are looking at is a path that other paths have not gone on before. It does not mean that a path that's later on the list is going on the path that we are on. But we'll hit that because we're going to go through all of them. For var e is equal to 0, e is less than existing e plus plus. Or we could say for each path that matches this condition, it'd be nice to pull out the path and could do that. Just say for each of our existing path in so if we find any, then we have to say var existing path junction is equal to the existing path visited junctions single equals that. If our visited junction let's just capture that. if the existing path our first path last junction cost is greater than or equal to existing path cost, paths to evaluate remove at I minus minus. And the reason why is because we want to go down, but we'll go back up, we'll hit the first one. And then we can say continue. Because we don't need to look at the others. Else, paths to evaluate, we remove existing path. Because we're cheaper. Index was outside the bounds of the array. Really? I'm shocked. Can you show me where? That's surprising. Oh. How? How would you ever get... Sorry. How would you ever get a path that had no existing junctions? Wait a minute. Wait a minute. Whoa, 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 whoa. This goes through each path to evaluate, right? Oh, we eliminated the... Yeah, okay, sorry. It took me a second to realize what I did. I think this should be 2. They're both in the same position, 113 east and north, right? So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Huh? Okay, now I'm kind of confused. We get our paths to evaluate, and that's 2 paths. Why does it skip like this? So we come into here, get each path to evaluate. Why does it skip like this? Sorry, this is really annoying. Our current cost is obviously less than this, so we say get next paths. What? What the hell? We have 2 paths at the beginning. The path to evaluate that we're doing here is going east. The path to evaluate is the one going east. We should have no paths. Why do we have 2 paths coming out of this? 513. That makes no sense. I got some logic screwed up here massively. I can't get past this. Okay, we're gonna go east. And our next position's 213. Do we have anything there? No, we don't. So we look north. And both these are saying that there is something there. It's a wall, so we don't do anything. We didn't find a wall, and we didn't add any new paths. We didn't have any new paths, so we break. No, that's right. We're going to look at the next one. So now we should be looking at 313. And 313 should not have anything. There shouldn't be anything above us or below us. And so we haven't found anything yet. We go on to the next one. And this is 413. Okay. We did find something, but it's not the end. But we did find a wall. Oh, crap. This one's killing me. Because we don't find anything north or south. We did find a wall. So we skipped that. But I think this needs to break if we find a wall. And we didn't find any other paths. How do I say this correctly? I get why it's skipping over because it's saying you're here. 0, 1, 2, 3, 4. Well, that's a wall, so we don't do anything. We look up and below. We didn't make anything, so obviously we got to move next. But we did find a wall. So if we found a wall, and new paths count equals 0, or not found wall, And new path counts as greater than 0. That feels like it could be simplified. What in the world did you just do? That's not what I meant at all. Nope, not going to do that. Not even going to do it. So if we found a wall and we don't find anything to the sides of us, then we stop. Or we didn't find a wall and we found a junction. We break out. Though still a little concerning. That we're getting this out of range. Oh my God, take that. Okay, so the path to evaluate is 113 going east. We should be getting no new paths out of this, right? Yeah, so we skip over this. The new path should be still nothing. And now the other path that we're going to do is 113 going north. And we should get 2 new paths out of this. Where 111 east and north. Okay, that makes sense. Okay. So now we add new 2 paths. Come down here. Oh, I think I know why. No. Yeah, it should. Adding gives you a new immutable array. How is that turning into 0? Well, I was going north, so let's go north. So we're adding a new path. At this point, we would find one because we're going to look east, we're going to look west, and maybe north, and we would. Fine, skip all this. Wait, the first one, now we get into this. Okay, so we don't have any paths. This has... Right, because we haven't visited any junctions yet. But we're going to add one to it, right? And so by adding, that's going to return one. If we go look at new paths now, visited junctions is 1. As it should be. But this visited junctions is still 0. We add another path. Now we've got 2. That has 1. That has 1. Perfect. So the next paths that we have here both have visited junction lengths of 1. Oh. I'm looking at the wrong thing here. So this has gone through all the paths and gotten next paths. We have to do next paths here. No, not next paths, new paths. We want to look at the first new path. And we want to look at that first path's junction. Now we need to say find existing paths in new paths where it's not equal to and that is that. We look at that existing path, compare it to that. If we remove it here. Otherwise, remove it. I was looking at the wrong thing, I think. That's the problem. Doesn't mean it's right. It just means... collection. Yeah, I was afraid of that. That's not entirely surprising. Because we are removing from this to that. I don't want to convert to link. I want to say our existing paths is equal to this to list or to array. It doesn't really matter. And then we say for what I was doing before is equal to 0, e less than existing paths lengths, e plus plus. And then we just do this. Except we have to get the existing path. Thank you. There. I get that. I was a little afraid with that for each if that was what was going to hit me. And it did. Finally. Okay, that's a step. That is a step. Not the step. That's another one. Now. Where is this? If you're wondering what I'm looking for, it's because somebody sent me this is what's called tab debt. Excuse me. One moment, please. Let me pull this off here. And let's see. Give me one moment here. At least I finally got 2 to pass. I mean, that's better than nothing, you know. There we go. That's what I'm looking for. So somebody was watching me do what I'm doing and said, hey, but then he said, this one, which is the same one, and this is what brought up the whole thing about spinning around and God. No, not. What the heck was that? There we go. Okay. That worried me a little bit because you notice it paused just a little bit. Oh, that was fast now. 90 more millis. And that did not pass for him before because the next two tests come from always give credit where credit is due. Okay. So let's put my thing there. Let's do that. Can we finally get an answer? No, we can't. God. All that work for nothing. It's infuriating. This is just getting infuriating. And I do not want help. I'm going to be explicit about that. It's still growing out of control. Even with everything I just did. I think it is a little bit more controlled now. But it's still... This is nowhere close to getting near the end of the map. Damn it. You know what I'm thinking of doing? Is skipping over this one for now. Just skip it. The problems aren't... they're independent of each other. You don't need to finish the previous one to do the next one. And I'm about ready to punch my fist through a wall with this one. And it's not worth it. Whatever I am doing in this, and I'm going to be absolutely adamant, please don't send me a hint. I think the best thing for me to do right now on this problem is just to let it go and move on. And I'll come back to it later because I do want to finish it, but I feel like I'm making no progress at this point. In fact, I think I almost made it worse. With all this work I did to try to be clever and cute, I don't think I did anything helpful. So I am going to do what I suggested. Got answers for part 1 of day 16, but it still bogs down on the real problem. And I'm absolutely sure I'm missing something brutally simplistic on it, but my brain can't see it right now. So the best thing to do is to walk away from the problem. So moving on to day 17. I am convinced this is the right thing to do. That said, I need to get some coffee. So I'm going to put my little note up here. This won't take long at all. I'm just going to run upstairs, get some coffee. 3:05. Okay. So I'll be right back. If you haven't subscribed to the channel yet, please subscribe. You don't have to like, but please subscribe. I would greatly appreciate that. So I will be right back in just a moment. Sorry, I just realized I was muted. I don't like leaving something unsolved, but there's obviously something with what I'm doing that I am missing the point. I am missing something. To not optimize this better. And that is a little disappointing, but oh well, we gotta move on, because otherwise I'm gonna be stuck on this forever. Day 17. Chronospatial computer. The historians push the button on their strange device, but this time you all just feel like you're falling. Situation critical, the device announces in its familiar voice. Bootstrapping process failed. Initializing debugger. Actually, I'm going to pause the music for just a second as I'm reading this. The small handheld device suddenly unfolds into an entire computer. The historians look around nervously before one of them tosses it to you. This seems to be a 3-bit computer. You know, they actually made those ternary computers in Russia or the Soviet Union. Well, do they actually have the link here? No, they don't. So let's say ternary computers. There is one. Yeah, Moscow State University. Seton or Seton. And a notable advantage over the binary computers, lower electricity consumption and lower production cost. So yeah, it was built most modern ternary computer. So they exist. Its program is a list of 3-bit numbers, 0 through 7. That's not a 3. Oh, not a ternary, 3-bit. Okay, I see what it's saying. So 0 through 7. But you learned something if you didn't know that there was actually ternary computers. The computer also has 3 registers named A, B, and C, but these registers aren't limited to 3 bits and can instead hold any integer. Well, that's architecturally specific. Do you mean a 8-bit integer, 16-bit integer, 32-bit integer, 64-bit integer? You know, what do you mean by that? The computer knows 8 instructions, each identified by a 3-bit number called the instruction's opcode. Each instruction also reads the 3-bit number after it as an input. This is called its operand. A number called the instruction pointer identifies the position in the program from which the next opcode will be read. It starts at 0, pointing at the first 3-bit number in the program. Except for jump instructions, the instruction pointer increases by 2 after each instruction is processed to move past the instruction's opcode and its operand. If the computer tries to read an opcode past the end of the program, it instead halts. So the program 0123 would run the instruction whose opcode is 0 and pass it the operand 1. Then run the instruction having opcode 2 and pass it the operation 3, then halt. Finishes, halts, whatever. There are 2 types of operands. Each instruction specifies the type of its operand. The value of a literal operand is the operand itself. For example, the value of the little operand 7 is the number 7. The value of a combo operand can be found as follows. What the hell? Combo operands 0 through 3 represent literal values 0 through 3. Combo operand 4 represents the value of register A, 5 represents the value of B, 6 represents the value of C, is reserved and will not appear in valid programs. Okay. The 8 instructions are as follows. So if the opcode is 0, it's an ADV instruction, performs division. The numerator is the value in the A register. The denominator is found by raising 2 to the power of the instruction's combo operator. So an operand of 2 would divide A by 4 because it's a literal value. An operand of 5 would divide A by 2 because it's the representation. I don't like how they say a literal and a combo is a literal. Like, what's the difference? The result of the division operand is truncated to an integer, which I think just means it's div, like div rem. What's the div? And without the remainder. The BXL instruction calculates the bitwise OR of register B and the instruction's literal operand. Oh, okay. I'm seeing what the difference is between these two. So this instruction says the operand is a combo operand. This instruction says the operand is a literal operand. That took me a second to realize what it was saying. So, okay. And then stores it in register B. So we've got a computer that's got registers. I think the best way to handle this is not to have an immutable model of a computer, but a computer itself that has a register. Yeah. The JNS instruction does nothing if the A register is 0. However, if the A register is not 0, it jumps by setting the instruction pointer to the value of its literal operand. If this instruction jumps, the instruction pointer is not increased by 2 after this instruction. Yes, the instruction pointer. Okay. Except for jump instructions, the instruction pointer increases by 2. So this is interesting. You have to take it as a literal sequence of what you could say, ints, bytes, if you really want to shrink this down in terms of the instructions, but you can't do them in pairs because a jump could actually jump you to where now okay, I get where that matters now. Okay. Oh, I missed this one. The BST calculates the value of its combo operand module 8, thereby keeping only the lowest 3 bits, then writes that value to the B register. Okay. That instruction is what we just talked about. And so there's an instruction pointer that we assume we just keep jumping by 2 unless this happens. This instruction calculates the bitwise OR of register B and register C, then stores the result in register B. For legacy reasons, this instruction reads an operand but ignores it. The out instruction calculates. For legacy reasons, yes. So you do have to read the operand. You still have to, basically you skip over what the operand is. It doesn't matter in this case. The out instruction calculates the value of its combo operand in module 8, then outputs that value. If a program outputs multiple values, they are separated by commas. So you're going to have an output that you're going to keep track of as you do this. Instruction works exactly like the ADV instruction, except that the register is stored in the B. The numerator is still read from the A register. The CDV, except it's the C register. So here's register C contains 9, then the program 26 would set register. And these give you some test cases. The historian strange device has finished initializing its debugger and is displaying some information about the program it is trying to run, your puzzle input. So you can set the registers to initial values and then you're given a program. Your first task is to determine what the program is trying to output. To do this, initialize the registers to given values and run the given program, collecting any output produced by out instructions. Always join the values. We'll join that at the end. We'll just output the values. Using the information provided by the debugger, initialize the registers to the given values and run the program. Once it halts, what do you get if you use commas to join the Nice. Okay, this one, I don't want to get cocky, kid. But that's interesting. It's like, oh, a small program, but yeah, let's I'm glad I did this. I'm glad I moved on, because otherwise I would have been just so frustrated trying to solve 16. And so we're just going to move on. I like moving on. Okay, let's get rid of all this crap. Right? And we'll do the same thing for 2 here. Don't really know how I want to do this just yet. Let's get rid of all that. Okay, so we've got a 17 here. So how do we want to do this? We could read the first line, the second line, the third line, and just assume that that's going to be, and then we find where the colon is, split on that, trim the right side, and then take all those and turn them into our inputs. So parsing this isn't going to be a problem. What we want to do, though, is parse this so that it gives us like the input. The input can have the register values in the program, and then we give it to a computer. So we want to have a public sealed record input, which has, and I'm going to say, I got the feeling these registers might be getting pretty big. And so you know what? We're going to make a huge computer. Because even though they're 3 bits, we're just going to make it happen. I like big integers. I like them. Register A, big integer, register B, and then big integer, register C. And then we want an immutable array, big integer, program. There. And then we're going to have a public seal class, not a record, a computer. And this one's going to have a public string output get. Okay, so we're going to actually do this. So we're going to say the public computer takes input. Okay. And we want to have a, well, we can't move the instruction pointer off of the list. But you know what? We're going to just keep going with this. Private big integer instruction pointer, which is equal to 0. Okay. And so when we take this input, we can say this dot output is going to be equal to this dot process the input. Perfect. We're done. Of course, we got to make it all happen now. So private string process, given the input. And actually, let's do something here. We're going to say this dot input is equal to input, because we want to also say, hey, what was it that we were given? Public input, input, get. And then the output can just read that. We don't have to pass it into it. So we're just going to say return string.empty right now. Actually, we're going to say this.input is toString. And it's yelling at me because it wants to be an expression body member. Fine. But at least this way we can have it return something. And yes, that's not being used for anything. Okay. We could do this. Public. Nah. So the first thing we're going to do here is... No! Stop it! Parse the input. Var register A is equal to input at 0 split on that. We want to, and then we want to get the first part of it. We want to trim it. And so this is going to be big integer.parse. Info. Okay, register B is going to be the next line. Same thing. Same thing with register C. And then the program is going to be, nope, it's going to be input of 4. Okay. We split on that, except, come on, do the right, oh my God. Why? And we're going to split that. We're going to trim it. And then we're going to split that on the comma. And then we're going to say select each one and say parse it. And then we're going to say to immutable array. Does that look like regex or what? That looks like a really crappy piece of code. Let's move this below. And now we can say var input is equal to new input, register ABC, except we want program. Cannot use local variable input before it is declared. You have to change names around here a little bit. There we go. Okay, so we get our input. Var computer is equal to new computer with input, and we'll return the computer's output. So this is actually going to return a string. There. And we don't have part 2 yet. Okay. So what are we outputting here? We're taking the input. We're going to say register A. We're just going to say what is that, right? Because register A. taking all the fun away. And we'll comment that out for just a moment because we're not using it. Let's go into tests. We just want to see, are we parsing correctly? Part 1. We only have one example, and that's this input. Okay. Or we're going to say 17. This should be equal to... Oh yeah, those are output things. That's right. Sorry, it could be longer than that. Which it won't. Actually, we can just delete all these for now. We know this is going to fail. We just want to see if it actually doesn't cack and gives us 729. Importing due to test failures. Yeah, I know that. What's the problem? Oh, for God's sakes. Really? Really? That's what you're complaining about? This doesn't build. And why doesn't it build? Oh, we can't show the errors. We're going to show you some stupid thing down here that says code analysis. Input conflicts in whole or part with the namespace system Windows input. Why in the hell is system Windows input coming into play here? This is the... Oh my God. You know what? We're going to call you computer input. There. And then we're going to say, here, computer input. How do you like me now? And then we're going to change this back to input. There. You like that? Good. Now, did it at least give us... Yep, cool. All right, so that did parse correctly. Okay, great. We got that going for us. Now the fun begins. So what we want to do now is cry. And why do we want to cry? It's, well, we don't. This stays an int. And the reason why is because we're going to be indexing into the array. Okay. So we want to say here is var result is equal to string.empty. Return result. We'll build that up. Actually, no. We want to have a new list of big integers. Because what we're going to do here is we're going to say string.join on a comma result. Oh, it will, trust me. Now what we want to say is while this dot instruction pointer is less than this dot inputs length, nope, program's length. But let's say we had 4. So we're going to be 0, 1, 2. And probably not quite that. Less than or equal to. Because if we had a program of 4, you always need an operator and an operand. Opcode operand. And so we want to be 0, 1, 2. So being 2 is okay. Because we could get... we can get 2 and 3. 3 is not, though. So the length of the program 4 minus 2 is 2. We could get the 2 and get the 2 and the 3. We could get the 1 and the 2. We could get the 0 and the 1. We cannot get the 3, though. So it's not just less than minus 1. We have to be actually this. I think that's correct. Okay, so now we get the instruction pointer. And we're going to say var opcode is equal to this dot input program at the instruction pointer. And then we're going to have operand plus plus. But plus 1 because that's a postfix. So we can't do that. Okay, so I think we got that being read in correctly. We're probably going to have to keep track of, did we jump? There are 2 types of operands, 8 instructions. Okay. So we want to do like a case. Let's have some const here. Private const int big int big integer adv that equals adv, that instruction. Okay. So now we say case if opcode is equal to computers adv. Actually, let's do this. I know you don't want nested classes, but we're going to do that. Private static class instructions. So now if we say computer instruction ADV, yay. Okay. If that's what that is, we do something. So let's get all the other ones in here first so we can build up that structure. BXL. That's 0. There we go. BST. That's 2, which it has an automatic conversion to. Nice. JNZ. 3. BXC. 4. Out. 5. And then BDV and CDV. BVD is 6. And then CVD. BDV. CDV. CDV. And that is 7. Okay. So you can have 0, 1, 2, 3, 4, 5, 6, 7. This is a blow up. Throw new, not supported. Exception. Invalid instruction. Invalid opcode. Should never hit this, but hey. So let's get all these in here. BXL, BST, JNZ BXC out BDV CDV. Okay, so now we've got all of our opcodes. And we don't have to read the op or rand in one of these cases. It's legacy, but we'll just read it anyway because we have. For most of them, we're going to need them anyway. Okay, so this one does division. The numerator is the value in the A register. The denominator is found by raising 2 to the power of the instruction's combo operator. Operand. And we could have something here to say, if it's a combo operand, private static big integer get combo operand, because I've got the feeling we can do some fun with operand switch. Oh, no, switch operand, right? Or operand switch. I keep forgetting. Damn it. So now we want to say 0 or 1 or 2, 2 or 3. This gives operand. What don't you like about this? Big integer is 0. What? You know what? Fine. If you're going to be this way, we're just going to do it the hard way. If operand is greater than or equal to big integer 0 and operand is less than 4, we return operand. Okay. Why are you... Yes, I know. Okay, so else if operand equals 4, we're going to need the registers. So maybe this is a function of the computer input. Where in the hell? Here. So let's put that in there. Public. All right, so if it's 4, we return this to our register A. And 5 is B. And 6 is C. Else throw new not supported. My God. Invalid operand. In other words, we should have never gotten here. Okay. So back to what we're trying to do here. So we've got that going for us. So now we say we want to do var is equal to big integer div rem, quotient and remainder. And we don't care about the remainder. The numerator is the value in the A register. So that is this dot input register A. And the denominator is big integer pow Is there a pow 2? Mod pow. Yeah, we'll just do pow. The value, which is this dot input, get combo operand of our operand raised to 2. Okay. The denominator is found by raising to the power of operand, which we got. The result of the division operation is truncated to an integer and then written to the A register. Well, that was fun while it lasted. I think what we need to do here is have our own public big integer register A get private set. So only the computer can change it. There. And we could do the same thing for the instruction pointer. We could say public int instruction pointers get private set. So everything is visible as the computer is doing what it's doing. Right, we get rid of that. And then we can also say, what is the program on the input? Public. There. So there. So now what we do is we're going to actually put this back onto the computer somewhere. We'll figure that out in a moment. When we get the computer input, we're going to say this dot register A is equal to input register A. Actually, we can do all this. This dot register B, this dot register C, and then this dot program is equal to I thought that would work. I think it works. This is doing a deconstruction on the input. So it's deconstructing A, B, C in the program. That's kind of slick. I like that. What is the problem here? We don't need to keep the input anymore. We have what we need. Okay, and so now we say the combo operator is, we have all of our registers, so we're good there. Except we can just say program now. Okay, cool. Wait, what? Wait, what? There. And now, coming back to this, we say the result of the division is truncated to an integer and then written to the A register. this dot A is equal to quotient. That one's done. The B instruction calculates the bitwise OR of register B and the instruction's literal operator. So if we do this one, this dot register B is equal to this dot register B. Is it XOR? Is this? And the instruction's literal operand. XOR. Yay! Sure. The BST instruction calculates the value of its combo operand module 8, then writes that to the B register. So this dot B is equal to this dot get combo operand mod 8. Nice. J and Z does nothing if the A register is 0. If this dot register A does not equal 0. However, if it's not 0, it jumps by setting the instruction pointer to the value of its literal operand. I'm starting to think that maybe big integers is too much. It jumps by setting the instruction pointer to the value of its literal. It jumps by setting the instruction pointer to the value of its literal operand. If this instruction jumps, the instruction pointer is not increased by 2 after this instruction. Then I don't get when you do 0, 1, 5, 4, 3, 0. How in the world it would jump to 0? That would be here. Oh, I see. Because I have the feeling what this is doing is it's at some point it's going to get register A to be 0, and so it doesn't do anything. So this literally says this dot instruction pointer is equal to your operand. But that's a big integer to an int, and it's not going to be able to do that. I mean, fine. The BXC is 4. Okay, Just making sure I'm on track. I'm going to go through these again. Measure twice, cut once. The BXC calculates the bitwise XOR of register B and register C, then stores the result in register B. So this dot register B is equal to register B XOR this dot register C. Okay. The out instruction calculates the value of its combo operator module 8, then outputs that value. So result dot add this dot get combo operator of our operand mod 8. The BDV instruction works exactly like the ADV instruction, except that the result is stored in the B register. The numerator is still read from the A instruction. So it's still read, except it's stored in B. And then this is the same as this, except we're stored in C. Okay. So we're still reading from A in those. Now, if we did hit a jump, var did jump, which is going to be false. Typically, we won't. So we get through to here. Now we're going to say if we didn't jump, this dot instruction pointer is equal to this dot instruction pointer plus 2. So if we're at 0, then we go to 2. What are you telling me to do? Sure, that works. Of course. All right, so we do this until we're done. So let's go look at our combo operator thing first. If it's a combo operator and we're either 0 to less than 4, so 3, that is the literal value that you're giving. Otherwise, if it's 4, it's A. If it's 5, it's B. If it's 6, it's C. And 7 is reserved. And will not appear in valid programs. So if you see a 7, it's invalid. There you go. Okay, ADV. The numerator is the value in the register. The denominator is found by raising 2. Oh. Holy crap, good thing I read that right. 2 to the power of this. And that has to be an int. Let's get those fixed. Okay, good thing see, you gotta read it twice. It's always worth reading twice. So, denominator is found by raising 2 to the power of the instruction's combo operand. Yeah, the result of the division is truncated to an integer and then written to the A register. Okay. BXL calculates the bitwise OR of register B and the instruction's literal operand, and then stores it. So what do you want me to do here? Compound? Sure, I'll compound that. Look at that little ligature there. It like combines right to the equals. That's cute. BST calculates the value of its combo operand, module 8, then writes that value to the B register. J and Z, if this is not 0, then we jump to the instruction, we make the instruction pointer the value of the literal operand, and we record that we did jump. The instruction pointer is not increased by 2, right? The BXC instruction calculates the bitwise XOR of register B and register C and then stores it in register B, and we don't do anything with the operand. The out, I know it probably reads a little bit without better that way, but whatever. The out instruction calculates the value of its combo operand, module 8. Right, did I just... Yeah. Sorry, the out instruction calculates the value of its combo operand, module 8, and then outputs that value, which we just added to result. The BDV works exactly like A, and so does C, except we store in either B or C. 2 to the power of that. Okay. So now what do we do when we run our test? We fail. Great. Invalid opcode. Well, that's cool. How do we get his 0, 1, 2? These are all big integers. And the program is a big integer. How do we ever say that an opcode is 0 and throw that? That doesn't make any sense. Oh, I know why. Else if... Jeez. This is why you write tests. Okay, that passes. $17. Screw you, day 16. So we say 17, part 1, giving the 17 input. And what does that do? Is that correct? It's been 84 years. It's been 84 years since I got a right answer. Oh, the dopamine, the endorphins, the whatever, they're flowing over me. Part 1 of day 17 is complete. All right. Can we do 18? Digging deeper into the device's manual, you discover the problem. This program is supposed to output another copy of the program. Unfortunately, the value in register A seems to have been corrupted. You'll need to find a new value to which you can initialize register A so that the program's output instruction produces an exact copy of the program itself. Are you kidding me? Okay. The brute force way comes to mind, but I've got the feeling that is rather stupid. Because look at that. That goes up to what? 59 million. There's something. I'm just gonna have fun with this for a second. I'm gonna. Is it always 0? Well, we're seeing they're always 0. So we get that. And now we just say while true. Var register A is equal to and what we're going to say is we want the result to be a string.join of on the program. That's what we want it to produce. And so we say that I'm just going to say int there. I could say big integer and just make this a 1. Okay. So we say we're going to give it a 1 as a register. We're going to give the computer a new input. We're going to say if computer.output is equal to the target result, we break out. Because we found it. Now, of course, I know if you're shouting from the gallery, like, this is stupid, Jason. I'm like, yes, I know it's stupid. Okay. Believe me, I know this is stupid. I'm just curious to see how stupid this is. I've already got an idea floating in my head of what the way you're really supposed to do this. But I'm not sure. And then we just say return I. So if we go to our tests, and we just put the 2024 in here, and we give the program input as that, what they're saying is that part 2 is equal to that. Of course, it's part 2 now. Does that even happen? Well, it happened. It took a second or two, but it happened. I guarantee you, program part 2 is going to probably take forever. Well, let's just see what forever really is. Right. So we're going to output here if I mod 1,000 is equal to 0. Console.write line I. We just want to get some idea as to just like how slow or fast this is taking. Nope. Oh, fine, whatever. Well, it gets to 1 million pretty quick. I mean, arguably, I could just let this run. Because we're at 5 million. You know, but this is obviously not the right smartest approach. Although it's kind of fun to just say, hey, go run a bunch of programs and see what happens. So let's see here. Come back, Jack, come back. I don't know why I have Titanic references in my head. But we're already at 15 million programs we've executed. Yeah, whatever. There's got to be a trick here, right? There's got to be a trick to say, given all of these instructions, and it's probably embedded in this 2024 and this and that. Oh, my computer calmed down for a second. I'm like, did it actually stop and find it? But nah. I'm just going to let this keep running, because if it gets the answer, it gets the answer, but whatever. How do you actually get it to being, if I look at the input, that's what we want it to be, right? So I'm going to move this down here. Come on. Can you please? Okay, there we go. So I'll just let that run and while this is going. So somehow we have to say, how would we be able to output something that by changing register A, you will get the same output. I can see there's somebody watching other than me. Is there a trick? I don't want the trick. I'm just going to be like, is there a trick other than just absolutely brute forcing the thing? And I mean, I could parse this up across different tasks, right? I could say task 1 goes like from here to here. Task 2 goes from here to here, and let them all go off and get it. But that feels a little, that feels like it's a little bit strenuous, just to say the least. I would imagine this has to stop somewhere around 2 billion on the search, because otherwise you wouldn't, saying it's an integer value and all this stuff. You want to keep them as integers, and integers are typically 32-bit. So we're already at 50 million, and we still haven't found it. And it doesn't take long for these to go. But how in the world would you be able to easily determine, given an input, that the program based on register A would give you the same answer? And like the Random.Code stuff says that, you know, every solution should be able to be computed on even average hardware in just a couple of seconds, if that. So this is obviously something where I am completely missing the point on this. Yeah, I guess you could look at this and say, okay, well, like this program is supposed to do something. Well, what would it do so that when we get to the output instructions that we actually start outputting these values? Right? That's my thought. Since our answer looks like this, but that's no, I'm sorry. No. Our answer, again, is the program. So it's this. So we want to say, if we're doing this instruction, it's always the output. How do we get the output to give us the value that we're looking for? And it's all dependent upon this register A. So maybe let's think about this a little bit. So we have a 2, 4. What would that do? This is kind of what we want our program to do, right? And of course, running through this, running through the program, it should be pretty quick, because the numbers that I'm giving for, as this is going through and giving it for register A, they go through extremely fast. So, you know, let's just stop this for a second. I can let this run over dinner or whatever if I need to. Let's do this. How many instructions does a program actually run? I guess is what I'm we want to have a public int processed instruction count. So as we go through this, oh, sorry. So what I'm curious about is if I come back to my solution day 17 part 2, where if we're doing this by 10,000, let's just write out Computer process instruction count. And I'm just kind of curious as to what that is. So it takes about 56 instructions to get through. As the number gets bigger, it does take longer. But not by much. I mean, we're already at 5 million. And we don't even get past 64 instruction. We don't get past doing 64 processes. Instructions. If you know what I mean, like executions, I guess. Executions of instructions. Instruction executions. Up to 10 million. We're up to like 90 million before, and we're already at 10 million. You know, obviously printing off only that helps. You know, if I said here 500,000. You know, we already get up to where we were before pretty quickly. Because we're not spending all the time. Even just processing these in little small blurps like that is helping. But let's again shrink this. Put that over here. So assuming that we'd have to do this 64 times, we have to basically say, hey, when I'm printing something out, I need that first value to be 2. So what would give me 2 as the first value? All right, so let's go through our instructions just to see if we can kind of pick up on anything. I'm just going to put these here because they're nice little guides. Yeah, we just hit 72. Six. So 2-4 gives register B A is equal to, we don't know. B is now going to be equal to four, and C would be equal to 0. Okay. Now we do 1-5. What does that do? It's register B XORed with register B. I'm sorry, register B XORed with the operand. So again, we don't care about A yet, but B is XORed with 5. I can't do that in my head. 4 XOR 5. No, I want you to XOR. You don't have those operations. Damn you. Standard graphing programmer. Thank you. So if I say 4, 5, XOR, thank you. So that would be 1. B is now 1. C is still 0. 7, 5. What does that do? This gets the value of A, which we don't know what it is. So A wouldn't change. B doesn't change. C becomes the quotient. And what is the quotient? It's the combo operator 2 to the 5. 2 pow 5. 2, 5. 32. So it's 2 to the 3, 5, register A. And that gets stored in C. So C is A divided by 2 to the 30. I'm sorry. 32. We don't know what that is yet. 0, 3. What does that do? This stores an A. So it takes A and it puts it in A. A is equal to A divided by 2 to the 3, which is 8. Okay. One comma 6. What does that do? It XORs B with, so it's still this, but B is XORed with 1 XOR 6. One XOR 6. 7. I know it's one or the other, the bits. That's how it works. So that's 7 now. 4, 3. This is B is equal to B XOR C, but we don't know what C is yet. So we need to say B is now 7 XOR this monstrosity. 5, 5. What does that do? We output something. And what we're going to output is what is in register B. So we output register B, mod 8. So we take whatever this value is, result equals that. We don't have anything with all these. But suddenly we're going to say the result is B mod 5. Now guess what that has to be? B's got to be equal to 2 mod 8. Right? I'm sorry, it's got to be not 5. Hey, the 5 says it's register B. So, but that has to be 2. So whatever this gives that has to be that. And then what does 3-0 do? 3-0, I think, pushes us, right? So as long as, yeah, now we basically keep all this, jump to the beginning. So obviously, I'm not sure if I can glean anything from this. Where are we on our program here? We're up to 121 million evaluated programs, and we haven't found anything that matches yet. But I might just let this run and come back after like dinner or something like that and just see what it did. This was a little interesting to try, but it obviously doesn't help. I mean, you can see how things flow through, but B has to be, for that first number, B mod 8 has to be 2. So whatever this is, this has to give a 2. Right? Or not, I'm sorry. It doesn't have to give a 2. It has to say whatever that is mod 8 has to be 2. And of course, as you keep iterating through this, oh, wait a minute. I was just curious. Okay, let's keep doing this. So now we have all this, right? But we say 2, 4. 2. Wait a minute. What does 4 do? It gets the value from register A. Oh, that screwed this all up. I did that wrong. Because a 2 operation gets the combo for A, and that's going to be A mod 4. It's now taking 80 loops to get to the answer for a particular input. And we're at 150 million. But yeah, I already screwed this up. Because B has to be whatever A is mod 4. And then 1.5 says B is this XOR 5. Yeah, this gets pretty gnarly in a second because you don't know what A is. Although this is true. So you need this to be, you need B to be a multiple of 2. You need B to be a multiple of 4. It's got to be something mod 8 gives you 2. And of course, that could be a whole bunch of numbers, you know. Yeah, it's not coming to me right now. If there's some kind of pattern that you can follow here to get what you want. Obviously the 3-0 here, no matter whatever garbage you get here, it's saying that we're assuming A is not going to be non-zero. I'm sorry, 5-5. I'm looking at the wrong thing. 3-0 just jumps us to the beginning. But we have to make sure that we cycle through this enough to get us these 16 numbers. Right? And so I'm actually thinking it's probably better to go int max value and go down, because the more iterations you do, the better. The 5 is the one that prints it. And the 5 says we print based on the combo operator, and the combo operator for 5 says it is register B mod 8. So we just need B to be mod 8. We're about to hit 200 million. So I'm kind of like, even though brute force would take hours, I bet it's going to work. That's my guess. It just... I could say put in 500 million as the answer, and is that too... If it's too low or it's too high, I could just say, we'll start at that number then and go through again, and does that equal it? That's kind of a crappy answer. But it would work. Right? Like if I say it's 600, so 600 million is too low. We could just stop this right now and say 600, that's too low. Okay, well, fine. This is cheating the system a little bit, but hey, whatever works, right? So if I come up here and I say this starts at new big integer of that, well, at least we know then that it's got to be greater than 600 million. And I could just wait another a minute and say it is like 12, return to 17. 1, 2, 0, 0, 0, 0, 0, 0, 0, 0. So is 1,200,000,000, is that too high or too low? I definitely feel like I'm gaming the system here, but excuse me. Is that a minute? It's still too low. So 1, 2, 0, 0, 0, 0, 0, 0, 0, 0. That's too low. What about 2 billion? I'm gonna say I'm gonna try 2 billion, and I'm gonna try 5 billion, because if it starts going above 5 billion, then it's like it's not an integer. It's something that you're gonna have to kind of use that thing that I did before, which is to say it's got to be like a 2, and then it's got to be, when you print that out, it's got to be some multiple to give you a this. So we're going to say 2, 4, 1, 2, 1, 2, 3, 1, 2, 3. So I believe, if I look at that right, yeah, that gives us the 2.4 billion. So we know that's at least the lowest thing to start on. Is it going to start going, "You're asking too many questions, young man. How dare you? How dare you do this?" What is 204? That is still too low. Wow. Well, what about 5? Now, just curious. What does... So I think we just saw our answer, which is this goes beyond an integer's max value. What about a unsigned integer? Is that going to be too low? Now it's like it's like, stop it, you jerk. I'm fine with that. I can wait. We know that 2.4 billion is too low. We don't know, though, if this is too high, and this will be the last one I do. If a uint max value is too low, then that means there's obviously something very, very that you have to kind of do this calculation that I was talking about in some way, or pick up that you have to say it's got to be like this times this times this times this times this value, so that that's what you're printing out. You need, when you get to, and again, this is all screwed up. Let me actually make sure that I don't follow that. Nope, we don't want to remove the line. We don't know what this is. We don't know what that is. And then we jump to the beginning again. So every time we run through this, we need this to run through one, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We need this to run through 16 times, but then the last 3-0 instruction needs A to be equal to 0. because then they'll jump off the edge and we're done. And we don't want to do any more. Because we don't want to get back to the print instruction. That would do a 17th instruction. Okay. So, actually, I mean, I just realized something. We need the 16th time when we print this out. Well, yeah, we need register A. Okay, register A needs to be 0. So if we do this, while we're waiting, I might as well just blast through this again. Make sure I do it right. 2 gets 4. 4 gets register A. Module 4, and we set that to B. 1, 5 says B is equal to itself, whatever that was, module 5. Seven 5 says register C is now register A divided by 2 to the power of, what is 5 here? B. Right? 7 says take register A, 2 to the power, in this case it's going to be B, and you store that in C. What does 03 do? 03 says we do that, except it's for the read from register A and we store it in register A. Fine. We'll just say A is now, because it's going to be the literal 3. So we're going to say it's A divided by 2 to the power of 3, which is 8. And we store that into A. Except we don't want to say A here, right? We want to say whatever that initial X value was. Of course, we've got to go through it even more because we need to well, that's fine. I'll just it's really, we want to find X. We don't know what X is. Okay, so that's X. B is going to be X mod 4. This is whatever X mod 4 mod 5. This is still X. This is still X. is that. This takes x. This is going to now say a is equal to x 8. This is 2 to the x mod 4, right? I think. Okay, what does 1/6 do? 1/6 now does register B module 6. Wait a minute. God damn it. 2 says we get the value of A and we module it by 8. Sorry, that's my bad. 1/5 is just that. Once the song is done, I'm going to put the value in and then see if we've got a bound or not. Okay, start over. 2 gives us whatever x is, because we get the value of A, which is x, mod 8. Okay, we don't know what that is. Why did it do that? 1/5 says register B is basically itself. Oh, this is XOR. I'm sorry, not mod, XOR 5. Let's clear these out because otherwise I've got damage going on. Yeah, so B is going to be that. Now 7/5 is we're taking register C is going to be equal to register A, which is still X, divided by something here, which is going to be 2 raised to the power of 5. B. And what B is this monstrosity. Okay. Not helping. Not helping. 0/3 is the same thing except it's done to register A. So register A is going to now be equal to A is going to be equal to X divided by 2 to the power of 6, which is register C. And register C is this ungodly big monstrosity. Four, 3. 4 takes B, XORs it with C, and stores it in B. So B is that. This whole thing, XOR that whole thing. And then 5, just prints it, right? Yeah, we take the operand, which is 5, that's B, and we just... So it's this whole thing. And then we do this. Not helpful. Not even in the slightest. Because at least I got the first part pretty quick. And now R here is, this is B, so it's this whole thing. Mod 8. Now, of course, you go to the beginning with this. Well, now A is something else, right? A is this whole monstrosity. So when you come back up here, it's that whole thing now, mod 8. So let's come to our answers. Let's put that in there. It's got to be 5 minutes by now. I did wait 5 minutes. That was definitely 5 minutes. And you'll notice how he said that was too low. So I'm going to stop right now because I've been streaming for almost 3 hours. And I'm just going to stop. And I'm going to say that there's got to be, like I said, I've said this so many times already, there's got to be a little trick here that says, if you just notice this, this is what will help you get to that minimum number. Because if you kind of work your way backwards, and that's kind of what I'm getting at is, you need to, when you print the last time, that has to end up here. Well, register A had to be 0. And if register A had to be 0 here, then what does that do as a consequence to this? And if that's true, then what is the consequence to this? Because to print out a 0 here, you know, to print the operand, which is 5, well, A doesn't have to be 0. Yes, well, no, it doesn't. It has to be a multiple of 8. We know that. It has to be a multiple of 8. Right? Because to get it to print out a 0 here, it could be a 0. A could be 0. Because 3 is going to look at... no, wait, I take that back. Because if we look at the program, it has to be a non-zero value to jump. So we know that A had to be 0 here. Or I'm sorry, here. A had to be 0. For this, A had to be a multiple of 3. I'm just curious. 3 times 5 times 5 times 3 times 6. 1 times 3 times. Well, it's got to be an 8 in that case, because you can't have a 0 printing out there. 7 times 5 times. But that's not, that doesn't, it's got to be at least a multiple of that, right? That's my thought. We don't know, but that's the only way I think that that's going to be able to print that out. So, and we know that at least that is the starting point. But we can't start at that because that's not necessarily a multiple of that. I'm just curious if we do this, what happens? Chaos. Well, that wasn't it either. But there's some reasoning around that, right? You have to have that you've got to have A be 0 at that point. Because you need it to actually... Well, no. I'm sorry. 5 prints out 5, which is B. So you don't care about what A is at that point. But whatever A is at this point, it has to be 0. To print 3, we've got to have B be a multiple of 3. Yeah, I'm gonna stop because that thing I just did there was not a good idea. But we know that that is too low. So we're just going to let that run. I'm going to let that run. I'm going to go get some dinner and I'm going to do some stuff. I probably won't do another stream on this until tomorrow. I am planning on doing a Splinter Cell stream after dinner. So if you're watching, thank you for watching. Please subscribe to the channel. I greatly appreciate it. With that, I'm going to sign off. Take care, and I hope to see you in the future.